All right, let's take a look at linear equations and how they all connect with tables and graphs and real-world models and scenarios and that kind of stuff. So, a linear equation is just something that graphs as a straight line, and often problems in the real world turn out to be linear problems or have a linear relationship. Here's our scenario. We're trying to book a 40th birthday party. We want to hire the restaurant and they've got a little room at the back. So it's $30 for the room, and then the banquet for the food would be $50 per person. So I could draw up a little table that represents this. I could say, look, all right, here's the number of people, and for each one of these, what will it cost? Well, if nobody turns up, it'd be not only a terrible party, but it would only cost me $30 for the room hire. I didn't have to pay the $50 per person because there is no person. If one person comes, once again, pretty crappy party, but it's only going to be $80, $30 for the room and $50 for that person. And you could see I could go through and work that out. For two people, it would be 2 lots of 50 plus the 30, etc., etc. And then I could complete my table. I've got a table of people and costs. If I have a look here, I can see that from 0 to 1 person, it goes up by $50. From 1 person to 2 people, it goes up another 50. And if I look right through, that pattern follows right through. This is the clincher. This is the crux of it. If this happens, if you've got what we call this constant difference, then it's a linear equation. That means it would graph as a straight line because I've got this constant difference as I go up through my table of values. Okay, and what we know about linear equations, or hopefully you remember from previous lessons, is they graph, or they have this form called y equals mx plus b, where m is the gradient and b is the slope. B is the y-intercept. It's not the slope, the gradient is the slope. Now, this is where it gets awesome because this constant difference is simply our gradient. It's the m value. So now I can see maybe I can start to build a linear equation that models my exact problem. If I've got a constant difference, it's linear. That constant difference becomes my m value in my equation. In other words, my slope. Going back here to my 0 value on the top row, that represents my b value or my y-intercept. So at 0 here, 30 becomes my intercept. So I've got a gradient, or m, of 50, a y-intercept, b, of 30, and that means now I can create my linear equation. This is what we call the gradient-intercept form of the linear equation. Y equals the gradient, x, and then the y-intercept. So I can put those numbers into that equation. I can say, all right, well, I'm going to create a space for the m, create a space for the b, and my m was 50, my b was 30. I've now got a linear equation that represents my table of values, that represents my real world problem. Okay, and if I wanted to put 1,000 people into my party, massive party, I wouldn't need to draw out a table of 1,000. I could substitute 1,000 into my x value here, and it would give me my y value, which would be my cost. Let's just take that one more step. I could also graph it. I can look at these pairs of values, 0, 30, 180, 2, 130, and when I've got pairs of that, they actually represent coordinates. So I can now graph them onto a Cartesian plane. So let's take the point 0, 30 and graph it. Okay, it will graph down here on my Cartesian plane. Let's take another point, the point 3, 180. It would graph here. Now, I only need 2 points to draw a straight line because I can draw a line that goes right through them. I'm going to take a third one just to satisfy myself, to be comfortable that there is in fact a linear relationship here. 5, 280, and I can see I can draw a straight line that goes right through those 3 points. That is the line y equals 50x plus 30. It's the model, the line that represents my banquet problem. Okay, I could extend that out and work out other values for different people. It's a linear model that represents my situation. One last thing as we wrap this up. I've just taken out there, I don't know if you can see, I've changed this value here because sometimes you'll just see them as x and y. Your table will just have x and y. Well, that's okay. The x value on the top we call the independent variable. By that we mean we can pick whatever number we want. I just happen to pick 1, 2, 3, 4, 5, 6, 7. It's independent. I could pick any value I want. But the bottom one, or the y value often in a table, we call the dependent variable, because this number will depend on the top one. So if I took this 1 and substituted it into this equation down here, my 50x plus 30, I would get 80. It depends on what I put in. So I have an independent variable and a dependent variable. If I, oops, I'm just going to zip back there a sec. Now, if I wanted to work out the y-intercept, let's say I was given a table like this, I don't have a 0 value for x, so I might need to create it. I might need just to put it in. So I can do that. I'm going to create an extra little column here. I can see as I'm working down my numbers, I've come down to the 0. Okay, and now what goes in here? What goes in this box? Well, to keep this pattern going, 50 every time, I'm going to have to come down 50 to get a value of 30 into that box. So if you don't have a 0 value, you might just need to slot in as many columns as you need to get down to an x value of 0, because once again, that's the point where the y-intercept happens. When x equals 0, so think about it on a Cartesian plane. When x equals 0, that is sitting on the y-axis. So this is the value that cuts the y-axis. Okay, when x equals 0. And good job. Look, we covered a lot there. But well done, guys. You've connected real-world problems, tables, linear equations, and graphs.